Welcome to BioVivacious. BioVivacious is a YouTube channel dedicated to clear fundamental concepts of biosciences. A polypeptide chain can take several configurations. Now, which configuration will really exist? That depends on the number of hydrogen bonds that exist. More the number of hydrogen bonds, it will be more stable. In an earlier video, when we were discussing about alpha helical structure, we have seen that there are hydrogen bonds existing between the first amino acid with the fourth amino acid. And that is consistent, which makes a very stable alpha helical structure. Today we are going to discuss about another kind of hydrogen bond formation between these polypeptide chain that is known as the beta-pleated structure. These structures were also proposed by Linus Pauling and Corey. They proposed it in 1951. Now, in order to understand this beta-pleated structure, let us draw a beta strand. A beta strand is nothing but is a primary structure of polypeptide chain. So what we will do, we are going to, this is important for us, let me rub this. What we are going to do is, we will draw the peptide bonds. So therefore here there is a peptide bond, okay, another peptide bond, another peptide bond. Okay, we have drawn 3 peptide bonds. Now what we are going to do is, we will draw the alpha carbon atom. So let us draw an alpha carbon here, and here is the alpha carbon atom. Let us link them. Okay, connected. So in this way, and here it will be, okay, in this way we can make, here there are 3 peptide bonds. So 3 amino acids are there. Now we know that it will exist in a plane. This will be a C alpha, and this is going to be another C alpha. If the plane will be from this C alpha to here, here, and this is one plane. And the second plane is going to be this, okay, this, and this. So the second plane, and the third plane you can draw like this, okay. So 3 planes are drawn. So because these are planar, the peptide bond is a planar, and you can see that though it is not, if the O was little more here, so it will be like this. The O is here. Okay, so you get an idea. If this is H is little more down. Okay, you get an idea. So how this will be forming. So basically, the point which we are trying to see that it is a kind of a planar structure, flat, and the bond angle is almost 180 degrees. So it becomes a flat structure in the case of a beta strand. Assume this is a beta strand. Similarly, many beta strands can be arranged. And many of these, this is another beta strand. What will happen is, this carbonyl carbon interacts with another amino group, and it will establish a hydrogen bond is established. And this way it becomes stable. Another hydrogen bond is established here. You can have a third strand. Hydrogen bond is established, hydrogen bond is established. So this way it will become a beta-pleated structure, a plate kind of a structure. That is another secondary configuration which is commonly seen in protein known as the beta-pleated structure. It is very important to see how exactly the rotation occurs. If the rotation around the alpha carbon is important in order to see it is a positive rotation or a negative rotation. That is determined from the perspective of the C alpha. from the C alpha, you observe the phi bond as well as the psi bond, whether it is moving in clockwise direction. If it is moving in clockwise direction, it is a right-handed helix. If it is in the anti-clockwise, it will be a left-handed helix. So depending on from the perspective of C alpha, we determine whether it is positive rotation or it is a negative rotation. In the beta-pleated structure, there is a repeated phi and the psi bond. Suppose you have a long stretch of a beta strand. Now, this can be arranged, a beta-pleated structure can be made in two ways. One possibility, if this long strand, you can bend it like this. Okay, you can bend it in this way. So therefore, this is the N terminus and this becomes the C terminus. Bend it. When you bend it, there can be hydrogen bonds established this way. In other words, if the polarity of this is N2C and here this is N2C. So therefore we say that this is anti-parallel. This is anti-parallel configuration that results into a beta-pleated structure. What is important about anti-parallel beta-pleated structure is, if the hydrogen bonds are formed between the CO of one amino acid with the NH of the next amino acid here, 180 degree. So therefore there is direct straight connection that makes anti-parallel beta-pleated structure highly stable. So let us draw a structure and then we will get clarity on how these hydrogen bonds are formed. For the sake of convenience, if the fully extended backbone of polypeptide chains are drawn on the board, these are going to represent the anti-parallel as well as the parallel beta strands. So let us make a distinction at the moment, so therefore there is no confusion. First of all, let us deal with the anti-parallel structure of a peptide bond. Please understand that the peptide bond, which we have seen in earlier videos, it is a planar structure. So you can compare, it will be plain like this. It's a planar structure. This is one amino peptide bond. Assume that this is forming an extended structure. So if you consider this is the form in which it will take, if the beta strand will form an extended zigzag structure of this way. Okay, now this zigzag structure, it will keep on repeating. That forms one strand. There can be a second strand also, if the second strand is arranged in this manner. And then there can be a third strand. In the case of anti-parallel structure, there can be minimum 6 strands and it can go up to about 15 strands in the case of an anti-parallel structure. Let us try to understand this extended structure of the beta strand. You can see that in the peptide bonds, this is one peptide bond, this is another peptide bond, then you have another third one, you have a fourth peptide bond. Look at the polarity. So therefore you can see that one amino acid, it begins from here and it ends here. This is one amino acid, then the next amino acid, then the third amino acid. They are arranged in that manner. You will see that in the phi and the psi bond, if the phi and the psi bonds are continuously arranged or shown in the structure. What is important is, if we remember this particular pattern, then it becomes much easy for us to represent the anti-parallel structure. So you can see that the polarity of this is N to C. The polarity is N to C. And the polarity of this strand, it is, you can see that it is moving in this direction. Therefore, this is N to C. It is absolutely an anti-parallel strand. How exactly are the hydrogen bonds formed? We have seen in the case of alpha helical structure, it is within the polypeptide chain from the first amino acid to the fourth amino acid. Whereas in this case, because of this extended form, that is not possible. What is going to happen is it will form a hydrogen bond with the neighboring beta strand. You can see that there is a possibility of a hydrogen bond being formed here. There is a possibility of a hydrogen bond being formed here. Another hydrogen bond can be formed and a fourth hydrogen bond can be shown here. Similarly, this will form another hydrogen bond with the neighboring beta strand. So therefore, this will form another hydrogen bond, this will form another hydrogen bond, this can form another hydrogen bond, this can form another hydrogen bond. So effectively what happens is, it becomes a plate-like structure. We call it a beta-pleated structure. It becomes like in the zigzag plate structure, extended form. So this is how the beta-pleated structure is formed, especially in the anti-parallel arrangement. Now let us understand the parallel beta-pleated sheets. So therefore you have one strand like this, and you have another strand this way, and this is N2C arrangement, and this is also N2C arrangement. Both are running parallel. Okay, both are running in the same direction. Now, bond formation, it is not, this kind of a bond formation is not possible. If the bonds are formed with a slight angle, one bond can be formed here. If the second bond can be formed here, another hydrogen bond can be formed here, and another hydrogen bond here. You see, they are formed at a particular angle. Similarly, with the next strand, these carbonyl carbon and the amino nitrogen will form bonds. So this is how the hydrogen bonds are formed in the parallel beta strands. What is important is to look at the bond angle. This particular bond angle, they are straight like this. You know that when there is a linkage of this kind, it is very tight. Collectively, these hydrogen bonds, the angle is 180 and it can be tight. So therefore, this forms a 180 degree angle. Whereas when it comes to the hydrogen bond angle in the parallel strand, this is 150 degree. It is like this is in the anti-parallel, it is like in the parallel structure, if the bond is being pulled in a different manner, diagonally. So therefore, with this, if the bond becomes slightly weaker in comparison to this. You yourself know that this is much more stronger than pulling from the sideways. So therefore, you will find these kind of arrangement mostly in globular protein, and such arrangements, that is the parallel arrangements, are mostly seen in fibrous proteins. A very important thing that we need to understand about the beta sheet is the distance between two amino acids. That distance is what we call a rise. In the case of alpha helical structure, this rise was about 1.5 Armstrong. Whereas in the case of a beta strand, remember the distance between one amino acid, this is one amino acid with the next amino acid, the distance between these two amino acids, that is roughly about 6.8. You will see that two amino acids are required to make so-called one turn. In comparison to, we have seen the varieties of turns that are being made in the alpha helical structure. Let us look at which all angle will allow the formation of a parallel structure as well as an anti-parallel structure. Let us create a table in order to understand that. This particular chart will explain to us which all bond angle helps the formation of a beta-pleated sheet. Either it is parallel or anti-parallel. Look at the anti-parallel strand. Okay, in order to do this, we need to compare the alpha helical structure which we have already learned. So if you look at the alpha helical structure, this is the alpha helical. So the alpha helical, what we are considering is 3.6. That is the alpha helical structure we are considering. If the general one, if the phi bond is going to be minus 60, and if the psi bond is going to be minus 57. You see, both are occurring in the minus direction. How many residues per turn? It is 3.6 residues per turn. So therefore we called it the 3.6 helical structure. And what is the rise per residue? The distance, that is about 1.5 Armstrong, and that will give a pitch of 5.4 Armstrong. So in order to form one helix, the length of one helix is going to be 5.4 in the case of an alpha helical structure. Now compare this with the anti-parallel structure. Now in the anti-parallel structure, you can see that it is the phi and the phi bond is in the minus 140. This will become important when we are learning about the Ramachandran plot. And we will be able to locate the location of the anti-parallel structure, the parallel structure as well as the helical structure of a protein by knowing these angles. That is where the significance is. So it is minus 140, and if the psi bond is plus 135, and two residues per turn, and if the rise per residue is 3.4 Armstrong. Okay, so and therefore since there are two residues, the pitch is going to be 6.8 Armstrong. In the case of a beta parallel structure, if the phi bond is minus 119, the psi bond is plus 113, there are two residues per turn. Once again, you have seen it in the previous diagram, and rise per residue is 3.2, and this is being repeated. This is repeated. Okay, now you can compare with the alpha helical structure. So this is a very crucial information with regard to when it comes to comparing and understanding the structures of alpha helical as well as the two forms of the beta helical structure. Please understand that there are times within a protein there can be a mixture of anti-parallel as well as the parallel structure existing within a protein. All that is possible. After looking at the structure of a beta-pleated structure, let us try to understand a terminology known as topology. Topology, we will discuss about how the connectivity happens and how it is represented. So we have seen that a beta-pleated structure is forming a zigzag, something like this. Okay, so it is forming a zigzag structure, extended structure. Now this structure, therefore effectively it is a flat structure. So we represent this flat structure as a kind of a ribbon. So therefore this is one ribbon. Now how do we show which is the direction of the N and the C? So we make this into an arrow. In this is the beginning. So therefore it is N, and the arrow is always shown towards the C terminal. Assume it is an anti-parallel structure. If it is an anti-parallel structure, you have the next sheet in this form. So it becomes very easy for us to connect it. So it is a simple loop can connect the anti-parallel structure. Very easy. But when it comes to a parallel structure, there is a slight complication. Let us try to understand that portion. So in the case of a parallel structure, so rubbing all this, in the case of a parallel structure, so okay, if the next strand is drawn like this is C and this is C, this is C, and the connection has to come here. If you consider the whole sheet on the plane of a paper, so let us represent on the plane of a paper. So assume it is on the plane of a paper, the whole structure. If the crossover will be, normally it is on the right handed side, the crossover. If the crossover is shown out of the plane of the paper, which means this out of the plane of the paper comes like this and we are connecting it here. This is out of the plane of the paper and it is a right-handed structure. Suppose if it is a left-handed connectivity. If it is a left-handed connectivity, what we are going to do is it will go underneath the paper. Okay, so therefore from here it will go underneath. We are not able to see what is happening, so therefore we represent it this way. So it goes underneath the paper and the connectivity as a left hand form it happens. This is how we represent topology, and this becomes important for us when we are looking at the domains of a protein, and this is very important. Basically, if you look at the beta sheets, we have seen it has a right-handed connectivity. So effectively it will look like this. Look at your right hand and the protein turns. So therefore this is the way the topology is normally represented when it is a right-handed antiparallel structure of a protein.